So what we have done till now is that we found all different types of loading on the battery pack. Then we found out different requirement of the materials. We designed base plate. We understood how to design the end plate. Pressure becomes important factor. Uniform pressure becomes important factor, especially for prismatic cells and pouch cells. Cylindrical cells are good because of its shape. Then we have analyzed what are the effect of the vibration that can happen on a battery pack, what are the things can fail. Then we compared the two different test standard followed for a smaller vehicle or battery pack, a small battery pack in India, AIS 048 and AIS 156. We have seen how in the test lab the vibration test takes place. How can we do all the vibration testing in the lab in all three directions, X, Y, Z. Now, this was the basically on the experimental side. Now, what I am going to talk next couple of minutes is about how to simulate, because in actual the vibration can happen in any direction. It need not to dependent on only perpendicular or horizontal. So before going through that, we'll understand what are the types of vibration, what we can simulate or can experience. So it can be defined basically in two domains, non-deterministic and deterministic. When we say non-deterministic, it's basically we don't know the amplitude of excitation. In deterministic vibration, we know the amplitude of excitation. That means it's well known. Now, these two vibrations can be further divided, these two types of vibration can be further divided into transient. When we wanted to see the response in small time scale, then we do the transient analysis. Harmonic is basically steady state analysis. So your excitation is fixed and then you see what could happen in the steady state condition. That means for the long duration, if excitation is same and it is running for the long duration, what can happen? That we do it in harmonic vibration analysis. And in the deterministic vibration, we know what is the magnitude of excitation. Then we have a spectral analysis, a spectral vibration analysis also, and that also comes a part of deterministic. In non-deterministic, it's like a random vibration, like road load or patches, which can appear anywhere. When that type of things we try to simulate, then it becomes random. If by virtue of statics, we are able to find a pattern, we are able to find out the excitation magnitude of non-deterministic vibration, and then then you can say a spectral. You are doing the spectral analysis. That means in each spectrum, what could be the failure. Here it's a random road excitation or patch holes. You don't know how good it would be there. But as soon as you are statically able to define the magnitude of excitation, then you can do with the deterministic approach. So basically this random and harmonic vibration is vibration analysis method, mostly steady state, long duration, and this transient analysis are basically a shock analysis method. You can do for impulsive force, crash. So that type of analysis is being done with the transient and the spectrum. The responses are in very small time interval, small time. Here it is steady state. Now I'll show you what are things we have done in our lab. So our objective is to simulate harmonic vibration test according to the standard AIS 048 2009 for one of our battery pack. The test temperature is less than 30 degree. simulation temperature constant is set to 25 degrees centigrade. Sinusoidal excitation supposed to be 3G. We have put 3G, 3 into 9.8 into 1000, 29400 mm per second square. Frequency range 30 Hz to 150 Hz. And that is to simulate the model in standard. So you see, your excitation is always low frequency. In high frequency you don't go, because most of the objects tend to have a natural frequency in the lower frequency range, something between 30 Hz to 150 Hz. What is our frequency, natural frequency? Around 2 Hz. Human body has around 2 Hz natural frequency. And that logarithmic sweep. So how do we do the vibration analysis? So initially we do the component level vibration analysis, component level model analysis, and then we do the assembly level model analysis. Now, why we do at component level? To find out the natural frequency. The model analysis, what it gives is the natural frequency of a component. As soon as we know the natural frequency, we always try to avoid that component should not get an excitation of natural frequency, or we try to shift the component's natural frequency by adding the stiffness or removing the stiffness to the range of this 30 to 150 Hz, so that we always try to move away from that range, because if anything happens in between that, my natural frequency will break. Because of the resonance, the component will fail. So the model analysis gives us a natural frequency range, and that we start with the component level. So the model analysis, what it does, it helps us to find the natural frequency and other frequencies where the component can resonate. Now, then we do the harmonic vibration analysis. That's basically a steady state with the known excitation. This helps us in determining and understanding that when my component will fail. Now, when we bring this component to the pack level, now we know the natural frequency of the component because of the model analysis at the component level. Now, if that frequency lies between the specified frequency of a standard or the lower frequency, then we try to increase the stiffness. How do we do? By adding the weight, by constraining it. And that is what we do in the pack, in such a way that its natural frequencies go away from the 50 Hz to 150 Hz or 200 Hz based upon that. What we have done is the side plate of a battery pack, that model analysis. So what we do in model analysis, we try to find out the natural frequency, and that natural frequency is nothing but stiffness divided by mass, square root of stiffness, root under K by M. Now, once we found out natural frequency, before that we provide the structure, whatever the components or the pack, with all its material for mass and stiffness calculation. Then only we can find out the through model analysis that natural frequency. Then we give the constraints, fixed or supporting constraint as per the design. Then we start simulating. What it gives us? The mode values and the mode shapes. When I say mode values, again the frequency where it can go to the resonance. Mode shapes are the eigenvectors, and that helps us in finding where should I put my accelerometer during the experiment. So this side plate, this is constrained by fixed volts and at these places. Now there are three modes here. Mode 1 occurs at 290.62 Hz. Mode 2 occurs at 490 Hz approximately, and the mode 3 at 740 Hz. However, these two may not be our interest because it goes beyond 0 to 200 Hz frequency range. This is of some interest. It's still outside my frequency range, but still it can have some interest. So these deformed mode shapes at a specific natural frequencies are function of structural properties and the boundary condition. Boundary condition here is fixed mode. What we can infer from this mode shapes? It gives us information about dynamic interaction between component and its supporting structure. Now, if I wanted to reduce even this mode shape, what should I do? So that is nothing but component and its supporting structure. Do I need to do something here? It helps in during the physical test, where should be my sensors placed to get the maximum deflection or the maximum sensitivity to be captured. It also helps in design change and providing additional constraints if required. So this is about one component. Now, once we have done this component, now we are talking about the full assembly. Now, if you see the assembly, the mode 1 is at 115 Hz, mode 2 is 202 Hz, mode 3 is 247 Hz. Now, all the three things falls within our frequency range. So we have to do the analysis for all the three frequencies. Now, we have not put the cell because then meshing and all the things will make it difficult. So instead of that, point loading as per the cell weight. Base is fixed and natural frequency is evaluated using mass and stiffness of the components, not at the pack level, based upon the mass and stiffness of the components which is there in that pack. The minimum at 115 Hz and the sixth mode at 302.6 Hz. Even we don't want to go this one. In fact, this 3 itself is more than sufficient. But as an extended analysis, we can go up to 302. So this vibration, what it shows here, if it is during the test or during the operation of the vehicle, if this frequency will come into the picture, the shape of the structure would be like this. So if my shape is coming like this in this mode 3, and if I want to avoid, I may provide additional stiffness by bolting it or by increasing the thickness of this plate. The harmonic frequency response analysis that we do next. So this gives steady state vibration for a range of frequency, one at a time. It can be used for determining which frequency causes most vibration. What we have seen in the last slide, 6 vibrations, and in that harmonic frequency response analysis, what it does? It gives us each of the frequency what would be the maximum deflection or which frequency will cause most of the problem. It helps a structure that operates at continuous speed like a fixed motor. It can also assess the random vibration environment. It provides the information about cyclic deformation as a result of vibration on excited frequencies. The frequency range 30 to 150 Hz as per compliance of AS048. In AS156, it's a slightly different. It also helps in evaluating the maximum deformation at resonating frequencies. What we have done from that, what we found that my maximum deformation is less than 1 mm. If you go back, what we have designed for? We have designed for the maximum deflection of 1 mm. Now my vibration analysis is also giving my maximum deformation wherever it is taking is less than 1 mm. So whatever we have designed is verified with the analysis. Now if this would have been 2 mm, in that case, we have to redesign the structure there by increasing the thickness or by changing the material or by changing the stiffness, by providing the additional support so that my deformation should not go more than 1 mm. So that's a plot here for maximum amplitude It's not very great visible, but you can understand this is around 1.1 mm. Yes, sorry, maximum amplitude is 0.01 mm here. So let's summarize this chapter. What are the things we understood? We designed a battery pack. We understand the various forces acting on this, and then we selected a material based on as-based methodology. Then we started designing the components for maximum deflection, maximum yield stress or yield strength. Then we also discussed about what would be the pressure requirement in prismatic and pouch cells, how to avoid that. Then we have seen another important aspect of mechanical design, vibration. We have discussed about the various vibration modes, model analysis, frequency response, maximum deflection. We have also compared the various standards being utilized in India, AIS 048 and AIS 156. So in nutshell, design of a battery pack should be safe even in the extreme conditions. It should be cost effective, lightweight. Every gram reduction in the weight helps in improve the range. It should be highly reliable, because this is what is going to give you the more number of cycles. If it is failing in between that, the upfront cost of the cell is you cannot justify. So it should be highly reliable. Various factors considered while designing a battery pack: material selections, loading conditions of base plate, end plate, side strips, bus bar and outer casing environment. What we utilize is Kirchhoff equation, differential equation, and their analytical solution using Rook's design data book. For end plate and side plate we have done. You can further start doing for outer casing, inner casing, bus bars, side strips. Then we have discussed various type of vibration, harmonic, random. So this comes mostly on steady state side, or we can say also it's basically a vibration analysis. And then we have also talked about transient and spectral, and that comes mostly for shocks and crash analysis. Various standards for battery pack testing, especially for vibration: AIS 048, AIS 156, and then SAE J2380. There are several other standards are also available. So with this, we are completing the mechanical design of a battery pack. Next class we will start thermal design of a battery pack. Any question?